Well, all right, here we are. This is chapter one of our course. And so we'll start with a very intense overview of different kinds of functions that we'll need throughout Calculus 1 and any courses that follow. So this is, if you open your book, you'll see that this is in chapter one. Um, the book has a lot of additional examples besides what you're about to see here. But basically, what we're doing here is following along with the textbook. And I have also added other new material that they may not have covered. Some of this might be reviewed from your earlier classes, such as pre-calc, for example, but it's all directly relevant. Everything in here is something you'll need going forward. So I've tried to make this chapter as comprehensive as possible so that we can have the best possible background for what follows. Okay, so we have a lot of work to do. So why don't we get started? And as you can see, we're going to look at functions. The first thing we need to do is define what we actually mean by the word function. And of course, a function is a relationship between two variables, one of which is defined as independent and the other is dependent. And of course, the reason why we use those terms is because the dependent variable derives its value from the independent variable. Now, before we do any discussion about functions, we need to take a step back and discuss the difference between relations and functions. So a relation is actually nothing but a set of ordered pairs. And of course, you've seen ordered pairs before using the XY coordinate system. Let me just show a quick example of this. Now, I just happen to have a tablet here so I can write anything I need on the screen. So with the XY coordinate system, of course, we have y in the vertical axis that is our dependent variable. X is the independent variable. And then we can plot points. For example, this point might be, let's say the point 2 comma 6, which tells me that 2 is the x coordinate and 6 is the y coordinate. You also recall that this is the first quadrant, this is the second quadrant, this is the third quadrant, and finally, this is the fourth quadrant. So a relation is really just a set of these ordered pairs. Okay, now if you're used to thinking about functions, with a function, we have an infinite set of points that are connected with each other, but with a relation, we may simply have a small number of independent ordered pairs. So in other words, a relation is not as complex as a function. So just a quick example again, suppose we were looking at these three ordered pairs, and these are the values. And so this is what we mean by a relation. Now, as it turns out, a relation can also be a function, but a function is not necessarily, not all relations are functions. Okay, so in other words, all functions are relations, but not all relations are functions. So we'll get through that in a second. So the first one we want to define is the domain. So the domain of a relation is simply the set of all the x values that we see. Okay, so here we have three ordered pairs. This is the first x. Let's think of this as x1, x2, and x3. And of course, this is y1 then, this is y2, and this is y3. So if you notice, the x's are 1, 2, and 3. And so the set that contains those values of x is what we mean by the domain of this relation. And it's just that simple. Now, what about the y's? Okay, well, the set of all the y values, again, y1, y2, and y3, is known as the range. Okay, so just remember the domain refers to all the x values of our relation, and the range is all the y values. Now, a function. We want to formally define now what we mean by a function. And we're going to do that in terms of relations. A function is itself a relation, but it has some required properties. In order to be a function, it must assign a single or unique value to every element in the domain. So now we're going to run through many, many examples of this. So the definition may not be as clear as it could be at first. No elements can be repeated in the domain, but elements can appear multiple times in the range. Okay, so we'll see what that means in a minute with some examples. First things first, we're going to use a special type of graph to illustrate relations. And so here's how it looks. Now we've got two circles. Now each of these circles represents a set. Clearly, in this case, set X contains the points 1, 2, and 3. Y contains the points 5, 10, and 15. The function itself is simply a mapping, as we call it, between the two sets. So what we've done here is this function assigns the value 5 to 1, 15 to 2, and 10 to 3. So this could have been written equivalently as a set of ordered pairs, 1, 5, 2, 15, and 3, 10. So the graph has its useful purposes. It's obviously, it takes up more space, but it's easy to see, a little bit easier to see the connections between the X's and the Y's. So we'll use this to help us identify whether or not a relation is in fact a function. Okay, now here's an example where this is not a function. Here's what the problem is. 1 is associated with both 5 and 10. And so already we know this is not a function. The problem here is that 1 is only supposed to be associated with a single unique value of y. The fact that it's associated with two values of y indicates that this is not a function. It's still a relation, but it's not a function. Now the others are fine. I mean, we have 2, 15, 3, 10. This is the problem right here. So writing this as a set of ordered pairs, we have 1, 5, 1, 10, 2, 15, and 3, 10. And you can see the fact that 1 appears twice is the problem. 1 is associated with both 5 and 10, and therefore it cannot be a function. Now, here's another one where there's a problem. What's the problem here is that 1 is not associated with any value of y. What we have here is 2, 15, and 3, 10. It is not a function. Because x is equals 1 is not assigned a value of y. So that rules this one out. So again, it's a relation, but it's not a function. Okay, a relation is simply a set of ordered pairs. That is the only requirement. A function, as you can see, requires that each element in the domain is associated with exactly one element in the range. Now, here's a more fun example. You can see that the domain and the range do not have to be numbers. You can see here what we have is when you walk into a Dunkin' Donuts, there's a big sign there telling you the prices of the different sizes of coffee. And you can see here, the small coffee is $1.50, the medium is $2.25, and the large coffee is $2.75. And you can see this is clearly a function because you can imagine drawing it like this. This would be X. This would be Y. Okay. So this is a particularly simple case. Obviously, each size has to be associated with a single price. You're not going to walk into the Dunkin' Donuts and have a sign that says small coffee is $1.50 and it's $1.75. That is not going to work. That would mean this is not a function. Okay, it has to be one price for each size. And that's how we know that this is in fact a function. So we can write it in a very interesting way. We can write it price, and this F notation means price is a function of size. And of course, that makes perfect sense. And if you notice, it doesn't work both ways. The size is not a function of the price. It's the price that is a function of the size. In other words, the size determines the price. The price does not determine the size. So that means that price is the dependent variable and size is the independent variable. And then we can set it up in a nice convenient chart. Okay, great. So you can see, yes, it is in fact a function. Now, how about this one? All right, so we got names and birthdays. Like I said, these do not have to always be numbers, although most of the time, of course, that's exactly what we'll see. In the majority of the cases that we'll be looking at, both the domain and the range are real numbers. So we've got names and we have birthdays. Now, these two have the same birthday. So the question is, does that mean that this is not a function? Well, it is. And the reason for that is because each name has one birthday, and that's it. Even though two people have the same birthday, if you were to draw this out, I don't know, I don't want to waste too much time with this, but what's going to happen is each x gets a y, even though two different x's can be associated with the same y, this still qualifies as a function. The fact that two people have the same birthday does not mean it's not a function. It would not be a function if a single person here was listed with two different birthdays. That is no longer a function. But here, the mere fact that everybody gets one birthday means that this is a function. All right, now, the domain of a function consists of all the values of x that can be substituted into that function. X values that would cause the function to be undefined do not belong to the domain. Okay, so in other words, depending on the function, it is possible that there are values of x for which the function is not defined. And if that's the case, these values do not belong to the domain. So in other words, it's not always the case that a domain always consists of all the real numbers. There can be values that do not belong. And we're going to spend some time looking at different examples of how to determine what the domain of a function is. Now, the range is basically what can come out of a function. Okay, the domain is what can go in, the range is what can come out. So for this last example, the domain would be all people. The range would be 365 days, or 6 in the leap year, because those are the only days in which there could be a birthday. There's only 366 to choose from. Now, evaluating functions is something we'll be doing quite a bit of as well. In other words, what we're going to try to do is write our functions not as ordered pairs, but as algebraic relationships. And the beauty of that is that it's very compact. It makes it possible for us to tell what is the appropriate value of y for every possible x that belongs to the domain. So here's a simple example. What if our f function here represents the price of gas? Now, you know that with a gas station, they don't normally offer you quantity discounts. You walk in the door, you drive in, and it says something like $3.65 a gallon. It means for every gallon you buy, you pay another $3.65. So this is a particularly simple function, and it's written as f of x equals 3.65x. This is equivalent to this saying y is 3.65x. Okay, so in this case, number of gallons is x. That's our independent variable. The price, or the cost, I should say, is our dependent variable. Oops. Okay, so in other words, now what we're going to do here is evaluate. Imagine sometime you drive into this gas station, you buy 10 gallons of gas. You want to know how much it's going to cost. Well, we plug 10 in for the x, and we end up with 3650. So what we've done here is evaluated a function, right? The function is the relationship between the cost of gas and the number of gallons you buy. And so once we know the exact number of gallons that we bought, it's easy to figure out how much it will cost. Or here's another one. I'm sure you'll run into something like this before. You'll recognize this as a quadratic function. We'll discuss this in great detail as we go along. Quadratic means that it contains an x squared term. So in order to evaluate this one, when x equals 7, we're going to replace all these x's with 7s. And so when you do that, you can see you've got 7 squared minus 3 times 7 plus 7, and we end up ultimately with 35. Okay, and it's just that simple. Now, of course, a lot of functions are not that simple. I mean, yes, you're just substituting numbers, but the actual evaluation process can get very messy. And we can use calculators to help us. Now, at this point in time, there are calculators, some of the very sophisticated ones, that can actually do some types of algebra, maybe even calculus. But for the most part, you want to do this by hand so that you understand exactly what you've done. Now, sometimes we can evaluate a function for demonstrating general results. Sometimes what we'll do is instead of using a specific constant, we'll use a variable like a. Okay, we'll see quite a bit of that as we go along. So in other words, in this case, whatever a is, the result will be 3a plus 7. Solving functions, we'll do quite a bit of this as we go along in this course. Solving functions. What we're trying to do is figure out what value of x corresponds to a given value of y. Often that value is 0, by the way. Like here's a good example of this. Here's a quadratic equation, and we'd like to know at what value of x it equals 0. Now, you might recall that a quadratic equation can be illustrated with a special type of graph. Let me just quickly sketch one out for you to quickly remind you how this works. Now, I'm just giving you a rough sketch. I don't know exactly how this will work, but it will look something like this. Okay, y equals x squared minus x minus 12. And of course, you'll recall from your travels that this is called a parabola. And it has that basic U shape. Now, just a quick review here, there's really only 2 types of parabolas you might run into. First of all, if you write out the quadratic equation in the following way, where a is the coefficient of the x squared term, b is the coefficient of the x term, and c is a constant, there's really only 2 cases you might run into when we have parabolas. It could be facing up, and this will happen if the coefficient of x squared is positive, and if not, then it will be facing down. If you notice, we're leaving out the case where at a equals 0, because if that happens, then this term will simply drop out and we'll end up with a straight line. It would then be f of x equals bx plus c. So here we're only considering parabolas. And so just keep in mind, and we'll see this again, that when the coefficient of x squared is positive, the parabola faces up. When it is negative, the parabola faces down. So for the most part, what we want to do when we solve for a quadratic equation is identify the 2 points where the function crosses the axis, or in other words, where y equals 0. These are known as the solutions. Or sometimes they're called the zeros, or even the roots. Oops, what did I do there? Of the quadratic equation. And because it is a quadratic equation, we know that there are two of them. The question is, how do we find them? Okay. And so you'll see as we go along, this is something that will help us with applications. You might, if you've had some economics background, you'll recognize that a lot of functions in economics are actually quadratic functions, like cost functions, for example. And what we can do is use this information to help us find the points where our output minimizes the cost of production, let's say, or possibly maximizes our profits. So this is an important application. Now, one way we can go about this is use a method called factoring. Now, factoring can work well with very simple quadratic equations, but in my opinion, you're probably better off using the second approach for the most part, which let me jump ahead a little bit here and remind you that the second, oh, I didn't even use it here, sorry. I'll just throw it in here right now because we'll get back to this later on anyway. Alternatively, we can also use the so-called quadratic formula. Now, assuming that we write our quadratic equation like this, you'll remember our old friend, the quadratic equation. Oh, yes. Looks like this. And the plus minus term right here indicates that we actually have two solutions here. Negative b plus the square root and negative b minus the square root all over 2a. The good thing about this function is that, or this formula is that it always, well, let's just say it's a very straightforward way of finding a solution. Factoring works great for simple cases, but for the most part, you're probably better off using this function. One thing I do want to point out, one interesting side note, is that when you look at a parabola, let's look at two different cases. Let's say we have an facing up parabola. Now, in both cases, A is positive, but here's the strange part about the second one. It never actually crosses the horizontal axis. So on the left-hand side, there will be two real solutions, meaning that they're real numbers. On the right-hand side, we're going to have two imaginary solutions. Now, for the most part, we'll try to steer clear of that in this class. Let me just quickly remind you what an imaginary number means. The letter I is used as a shortcut or shorthand for -1. This is what we mean by an imaginary number. And if you combine that with a real number, let's say a plus bi, this is sometimes called a complex number. It consists of a real term and a imaginary term. I don't know. We usually hear the words used interchangeably, imaginary and complex, but technically, the second one should be referred to as a complex number. The first one is what we mean by an imaginary number. So, even though we're guaranteed to have two solutions for this parabola, the one on the right means that we'll have imaginary solutions. And how does this happen, by the way? Because this expression, in the case of the one on the right, b squared is less than 4ac, so therefore we have a negative number under the square root sign, and that's how this comes about. Okay, but for all the other cases, that's not going to happen. All right. Anyway, let's go back and revisit the concept of factoring. I started with a simple case. In fact, if you remember this very well, you might be able to do it in your head. What you're really doing is saying, listen, we're taking a quadratic equation and breaking it up into a product of two binomial terms. Okay. because there's two terms in each set of parentheses. Now, if you multiply these out, let's do that real fast. You might recall this wonderful technique you learned somewhere along the way called FOIL. Here's F, the first in each set of parentheses, each term, each binomial term. Outer would be these two. Inner would be these two. And this would be last. And when you combine these, this is the result. So in the case of our example, this tells me that m plus n is -1, mn is -12. So what we actually have here is two simultaneous equations, which we can solve. There's a way of doing this I think is quicker, the quickest. Oh, there's so many ways we could do this, but what I think we should probably do here is this. Well, let's focus on this part. What we ideally like to do is try different pairs of real numbers, integers in this case, whose product is -12. Okay. We don't have to bother with the others. We don't have to bother with, let's say, ratios or anything like that, because the coefficient of x squared is just 1. So, for example, we had 1 and -12, -1 and 12, 2 and -6, -2 and 6, 3 and -4, -3 and 4. Now, what we're looking for is the one unique pair of constants with a product of -12 whose sum is -1. That would be this case. Okay, in other words, these two satisfy both equations because they add up to -1 and they multiply out to -12. So this implies that this product is equal to the original quadratic equation. Now, let's just quickly prove this with FOIL. Oops. Let me just remind you what the original equation was right here. And so we'll just use FOIL to prove that this is correct. Here's on. And then last would be these two. And when you combine all these, you'll see that we can combine these two. Now, how does that help us find the solutions? Because now we know that whatever this looks like, this parabola, if either of these by itself is equal to 0, the entire product is equal to 0. So we can set each one individually equal to 0. So that means those are our two solutions. These are the points, -3, 0, +4, 0. So these are the solutions of this equation, meaning those are the two values of x where the function has a value of 0. So that's how we solve for a quadratic equation. Now, we could also use the formula I showed you earlier. In fact, why don't we do that right now? Just to get some practice. I don't know how long it's been since you had pre-calculus, but there's nothing wrong with a little review. So remember, the quadratic equation, we write it out in the general form. So here a is 1. The coefficient of x squared here is implicitly 1. B is -1. And C is -12. All right? We're going to have -1 plus and minus -1 squared minus 4, 1, -12 all over 2 times 1. Okay. Now, I think I can copy that. Yeah, there we go. Yeah, sometimes this tablet works very well. Sometimes it's a little stubborn. Okay. We have 1 plus 48. Okay. So that means we've got 1 minus 7 over 2 and 1 plus 7 over 2. And that means we have -6 over 2, 8 over 2. Oh, yeah, there we go. So we've done it. So either way you look at it, the solutions to this quadratic equation are 4 and -3. All right. So, and here's the graph. I did this, by the way, I did this graph in Excel. Excel is a great tool, but it doesn't always have the best math graphs. So what you're going to notice as you go along through this course is that some of these graphs are done in Excel. The ones that where Excel isn't really adequate for the job are coming from the special website I'd like you to see. It's called Symbolab. It's an online scientific programming package, I guess. And what it'll do is help you solve math problems, but it also gives you graphs. So if you say to it, listen, what is, whoops. All right, it's being a little stubborn. All right, here we go. So what I'm going to do is hit the go button. And then I'm going to ask it for the graph. And this is what it really actually looks like. So you can see if you hover over the key points, the solutions are 4, 0, -3, 0, as we predicted. It also will have a lot of other useful information that we will address later on. For example, the minimum point on this graph, that type of thing. And it also will cover a lot of other useful things like the domain of the function, which we'll discuss very soon. It has all kinds of useful, helpful information. Even if you didn't ask for it, it's saying, listen, by the way, did you know that the domain is this, this, or that? So it's a very helpful function or website, I guess, and it's free. Now, they have a more advanced version that you can pay for, but the free version is just fine. Okay, so I just wanted you to see this because it might come in handy. Now, if you're ready for a more advanced package, and I'm just going to mention this because you can get this for free as a college student. There exists something much more sophisticated, which you normally have to pay a lot of money for, but it's called Mathematica. And it's basically a very powerful version of Symbolab. The difference being that you really have to put in the time to learn how to use it, but it's insanely powerful and it can create unbelievable graphs. So they have deals with just about every college in the country, where as long as you're a college student, you can download this and use it for free until you graduate. They're hoping that when you graduate, you won't be able to live without it and you'll pay for it. So if you need it now, you might want to at least look into it. And I know for a fact that SUNY Purchase has this available to the IT department. So, if you're willing to learn, like you can see that there's code here, there's steps, there's commands, you have to do all that yourself. Whereas if you notice in Symbolab, all I had to do was actually type in the function and all the stuff comes along for the ride. So the trade-off though is that it's more complicated than Mathematica, but it's incredibly powerful. Used by a lot of professional mathematicians, let's put it that way. All right, so let's get back to it. How about the intercept of a function? In other words, where does it cross the vertical axis? Whatever that point is, the x-coordinate is 0. The y-coordinate is whatever the intercept happens to be. Okay, we'll call that 0, f of 0. For that same one. Now you notice that it has to cross the vertical axis at some point. No matter what the sign is, even this one on the right, even though it doesn't quite cross the horizontal axis, it has to cross the vertical axis. And by the way, even if it starts on the extreme right-hand side, it continues forever. So it does eventually have to reach the vertical axis. So all parabolas have a vertical intercept. The question is, where is it? So it's a simple thing. All we have to do is substitute 0 for all the x's. It couldn't be any easier. And so in this case, you can see the intercept is -12. And if you go back to Symbolab, you'll see that it's right here. No, it's not. Sorry, here it is. 0, -12. Okay. Beautiful. Now, of course, there are many different kinds of functions. One that can be very useful is something called a one-to-one function. Now, what is this all about? You remember before we said that that function that we identified between people and birthdays is a function, even though multiple people can have the same birthday, each individual only has one birthday, and that's all that matters as far as a function is concerned. But there's a special class of functions which are even more restrictive than that. And that means that each x can only go with one y, and each y can only go with one x. In other words, it goes both ways. So the birthday case is not a one-to-one function because multiple people can have the same birthday. So what would be a good example of an actual one-to-one function? Well, that would be social security numbers. Here's why. Because the same people I showed you earlier, 2 of them had the same birthday, but no 2 people can have the same social security number. So that means that if you drew something like this, let's say a simple case, it must be the case each x goes with a single y, each y is associated with a single x. It has to go in both directions. And that qualifies this as a one-to-one function. And, one-to-one functions have certain useful properties, which we'll see later on. It's good to know if a function is one-to-one. Graphically, there are rules that'll help us identify whether or not a function is one-to-one just by looking at it. So here's an example. F of x equals x squared. Clearly, this is a parabola. The intercept, now I didn't draw that as well as I could have, but let me give that another shot. The intercept is the origin 0, 0. Okay. In others, it doesn't have any negative values. Now, here's the thing, though. It clearly is a function. And by the way, you might remember there's a graphical test for whether or not a relation is a function. Let me just mention it to you right now. Uh, this is the so-called vertical line test. I'll write this in the next slide. Hold on. Okay, so according to the vertical line test, if a vertical line crosses through a graph more than once, it is not a function. It is only a relation. All right, so let me show you a quick example of that. So let's say here clearly this one is a function. No matter where I put a vertical line, it's only going to cross once. But let's say it's something like this, which is, you might recall, is called a locus. That's going to fail the vertical line test. Okay, let me fix this up. Yeah, that's what about the eraser? The vertical line test. And therefore is not a function. It's a relation, all right, but it's not a function. This one passes the vertical line test. And that implies that it is a function. Okay. Now, why did I bring that up now? Because we'll see here in a second that there's also an equivalent test for one-to-one functions. So if you look at this one, the problem here is that x equals -2 and x equals +2 are both associated with 4. Okay, so this is like the birthday case. You have multiple people with, if x are people and f of x is birthdays, multiple people can have the same birthday, and that's a function, but it is not one-to-one. Okay, so how do you know that? Well, we have this other alternative test called the horizontal line test. So what that means then is that if we can draw a horizontal line through a graph and it touches more than once, oops, hold on a second. This one fails the horizontal line test. So while it's still a function, it is not one-to-one. Okay, that one is not one-to-one. Now, a straight line like this one is clearly a one-to-one function. I mean, no matter where you draw the line, you see, it'll never cross more than once. Here's another example of a one-to-one function. Y equals x cubed. This is what it looks like. Across the axis of the origin, it curves up, and you can see it definitely passes the vertical line test. And it is therefore a one-to-one function. All right. So now, by the way, you might wonder why this is so important. Among other reasons, it'll turn out we'll discover that any function that is one-to-one is guaranteed to have an inverse. So that's a huge help in our if we're looking for an inverse for a function. If we know right up front that it's guaranteed to have one, that will help us find it. Okay, now we're going to go. This is where we're going to start looking at the different kinds of functions that we may encounter in the course. There's quite a long list, but you're probably already familiar with all of these, but we want to quickly go through them, remind ourselves what they look like and what kind of properties they have. In particular, we were interested in looking at their ranges and domains. We want to understand how they are graphed, but right now we want to focus our attention on their ranges and domains. Okay, so you can see they all should look familiar. The constant function, identity function, absolute value function, quadratic, which we just discussed, cubic. Cubic, by the way, just means that there's an x cubed term in it. Reciprocal functions, or reciprocal squared, square root, and cube root. Okay, these are all very familiar to us. We're going to get to the more complicated ones later on. And down the road, we will start to introduce trig functions as well, which are somewhat familiar with, of course, but that will wait for several chapters. The trig functions are extremely useful in certain disciplines like engineering and architecture and design and things like that. In other disciplines, we don't see it ever. Like I can tell you from experience, in applied areas like finance and economics, we just simply don't run into the trig functions very often, if ever. So, but if you're in physics, in doing something involved with physics or engineering, you'll see them all the time. And we will be covering them because you'll certainly need them in Calc 2 and later other courses as well. Anyway, a constant function is just what it sounds like. Y is some constant. Y equals 3, for example, would be an example of a constant function. Now, if you notice, you recall from earlier math classes, there's no slope here, is there? All we have is a horizontal line. Whatever C is, that's it. It's literally just a flat line that cuts through the point 0, C. The slope for this line is 0. Remember, the slope is defined as delta y over delta x. But here's the thing. If you notice, y never changes. So therefore, this is just simply 0. You might also recall that a vertical line, the slope of a vertical line is undefined because delta x is 0. We have division by 0. So you might remember those two special cases. A flat or horizontal line has a slope of 0. A vertical line has an undefined slope. So here's an Excel graph for this. X equals y equals 5, or f of x equals 5. And it's just literally a straight line. It's not the most exciting function in the world. You don't run into this very often. Now, the identity function. It just means that y always equals x. Okay, so it's a very well-named function, that's for sure. And what that looks like is this. Okay, so no matter what point you're looking at, if y, for example, is 4, x is also equal to 4. With 0, 0, as you can see, no matter what point you're looking at, the two are equal to each other. The slope is equal to 1. All along this line, because it is a straight line. You might recall that a straight line is written as mx plus b. In this case, m is 1, b is 0. Therefore, the slope is 1. Now, here's one that you maybe haven't seen in a while. The absolute value function. What it basically means is that you're essentially ignoring the sign. Okay. Now there's a formal way of writing this. Let me just show you what that looks like. This is sometimes called a piecewise continuous function. It means that there's two distinct regions to it. For positive x's, the absolute value just equals x. For the negative x's, the absolute value is the positive version of that, which means it's the negative of the original value. Okay, so you might recall too that because of this, the graph has a very interesting shape. There it is. It's like a big V. And if you notice, it's only defined in the first and second quadrants. Okay, you cannot have any values in the third or fourth quadrants because those have negative numbers. So, by the way, if you think about this carefully, you'll recognize that while this is a function, this one is not one-to-one because it fails the vertical line test. I'm sorry, it fails the horizontal line test. It's a function, all right, but it's not one-to-one. Now, here's the one we've been talking about all night, the quadratic function. This is the basic form. It looks like, it is a parabola, which, yes, you could define it as a bowl. It faces up or down. As I said before, if A is positive, it'll face up. If it's negative, it'll face down. Here's another example. X squared minus 2x minus 15. And you notice now, it's hard to tell from this graph, but we could, if we chose, solve for it by using the quadratic formula or factoring, and we would identify these 2 points as our solutions. I don't know. Why don't we do this just for the fun of it? Practice is always a good thing. That's my opinion. So that means that in this case, A is 1, B is -2, and C is -15. Now, there's no guarantee that these answers will be nice integers, but we know that they'll be real numbers. How do you know that? Because you can see that the graph crosses the horizontal axis. So we'll not encounter any imaginary numbers here. Okay, so we have +2 plus and minus. So inside here we have 4 plus 60. Whoops. And of course, radical 64 is just 8. So we're going to end up with oh yeah, what do you know? -3 and 5. Nice integers. -3. So that means this is -3. And this is 5. Perfect. All right. Here's a cubic function. Now, these are a little bit trickier to visualize what's going on. They can take different shapes depending on the signs of these coefficients. But this is the typical cubic function. They all have that unique way of curving up. It's like a roller coaster where it's going up, it's slowing down, and then suddenly it goes up. Except that it will not eventually come down like a roller coaster. It's going to rise forever. But if you change the signs, you'll see that the behavior can get very interesting. But we'll come back to this later on. You can see also that it's 1-to-1 because it certainly passes the horizontal line test. Now here's where it gets a little tricky. Reciprocal function. Now here's the problem with the reciprocal function. We cannot allow x to equal 0. Okay, so what that means then is that 0 is not part of the domain. Because 0 would lead to division by 0. So what exactly does this thing look like? Now, of course, you can tell this is Symbolab. What's happening here, if you notice, is that the domain does not include 0. Guess what? The range also excludes 0. You can tell by looking at the graph. The vertical red line, these pink lines are the function. You see they're getting closer and closer to the vertical axis. They'll never quite reach it. And the same thing is true of the horizontal axis. So you might recall that the vertical and horizontal axes have special names. They're called asymptotes, meaning that those are lines that the function will approach but never quite reach. Now, you might wonder about that range. What this is saying is that there's no value of x that can cause this ratio to be equal to 0, and that's why this is happening. So the domain includes all real numbers except 0, and I can write that in a very special way. I'm writing it as a union of two intervals. All the real numbers from -infinity up to but not including 0, combined with all the real numbers from 0 up to infinity, not including the 0. The fact that these are round indicates that this is not part of the set. The range is the same. And we'll go through this again in great detail later on. I just want to throw it out there right now because we'll use this notation all the time. So we say, the terminology here is that there's a discontinuity in the graph, which basically means that if you were to try to draw this with your pen, you would have to pick up your pen at some point and move it. A continuous function means basically your pen would never come off the paper. So there's a break in the graph somewhere. We call that formally a discontinuity. Now, this is a similar situation, except x is squared, so the graph will look a little bit different. Well, let's see. Oh, you know what? I'm not sure. Oh, you know what? I'm not positive this is the right graph. Hold on a second. No. Something went wrong here. Sorry about that. I'm glad that I noticed this right now. So I can correct this. Yeah, that's what I thought. That's what it actually looks like. Okay, let me just get this in there. I'm going to post the corrected version onto Moodle. I don't know how that happened, but we caught it, and that's the important thing. So what you notice is that there's still a couple of asymptotes in there, the same asymptotes, but what's different is that the graph is restricted to the first and second quadrants, because no matter what number you square, it has to be positive. So we cannot have any negative y's. Once again, we have a discontinuity, and we also have two asymptotes. Okay, so I'm going to stop right here. So I will make another recording, of course, which I'll call part 2. Right now, if you notice, when you get to this recording, you'll see that it's been labeled chapter 1, part 1. I don't know how many parts we'll need for each chapter, so I'm just going to start labeling it 1, 2, 3, etc. until we're done. So this way, I think an hour is a good time frame to have a lecture, because 2 hours is kind of a long time, so I'd rather break it up into 1 hour slots like this. So that way you can watch an hour and then do something else, or you can watch the second one. But my plan is to have 1 hour at a time, and then you'll know which is which by the part numbers. Okay, so in other words, tomorrow I'll be recording part 2 of this, and then we'll go through the entire chapter. I don't know how many parts there'll be. There could be 7, 8, 10. I don't know. But so we'll do this 1 hour at a time. Okay? This way you can watch it, you can get something to eat, and then come back and watch part 2 if you want. So we'll stop it right here. And then tomorrow sometime I'll record part 2, and then I'll continue to record these so that each week we're covering the right amount of material. And so we'll stop here, and then in part 2, of course, we'll pick it up with the next round of functions. The next one is the square root function, and then we'll just take it from there. Okay. So, all right. So I hope this is good review for everyone, and I'll see you in the next part.